All right, let's dive into a family of chemical compounds that are basically woven into the very fabric of our modern world. I'm talking from life-saving medicines to maybe even the screen you're watching this on. They are the haloalkanes and haloarenes, truly the essential building blocks of organic chemistry. But here's the thing, it's not all straightforward. What could possibly connect a drug that cures typhoid fever with a chemical that literally sparked a global environmental crisis? Well, the answer is this exact same family of compounds. And that, right there, is the fascinating two-sided story we're getting into today. And I mean, these compounds really do have a dual identity. On one hand, you've got amazing stuff like chloramphenicol, a powerful antibiotic. Even our own bodies make one, thyroxine, an iodine-containing hormone that's absolutely crucial. And in surgery, there's halothane, a reliable anesthetic. But this same chemical family also gave us DDT, a name that, well, it tells a much more complicated story. So, here's the game plan for today. We're going to start with why these halo compounds matter so much in the first place. Then, we'll meet our two main players, the haloalkanes and the haloarenes. We'll dig into how they're made, and finally, we'll explore the powerful and sometimes perilous world of the polyhalogen family. Okay, first up, why should you care about any of this? Well, to put it simply, these compounds are like the ultimate multi-tools of chemistry. They're found in nature, they're made in labs, and they're not just used as solvents. More importantly, they're the perfect starting point, kind of like chemical Lego bricks, for building an incredible range of other organic molecules that we rely on every day. So, let's meet our first key character. Think of these as the simpler, more straightforward members of the family, the haloalkanes. The definition really is all about the bond. In a haloalkane, you have a halogen atom, fluorine, chlorine, bromine, or iodine, and it's attached to something called an sp3 hybridized carbon. Just think of that as your standard, stable carbon atom that forms 4 single bonds. It's the backbone of all those simple chains and branch structures you see in chemistry. And that specific bond, that's what makes a haloalkane a haloalkane.
Now, we can sort them into categories pretty easily, just based on where that halogen is sitting. If its carbon neighbor is bonded to only one other carbon, we call it primary. If it's bonded to 2 other carbons, that's secondary. And 3? You got it, tertiary. And this isn't just for labeling's sake. This structure directly tells us how reactive the molecule is going to be. Turns out, the tertiary ones are the most reactive of the bunch.
Now, check this out, because this is where it gets really interesting. Look at how that carbon-halogen bond changes. As you go down the periodic table from fluorine to iodine, the atoms just get bigger. And you can see it right here in the table. The bond length gets longer and longer. So what happens when a bond gets longer? It gets weaker. See the bond enthalpy? That's the energy you need to break the bond. It drops like a rock, which means it's way easier to snap that bond with iodine than it is with fluorine. And that has huge implications for how these things react. And that trend affects other properties too. This chart shows us that as that halogen atom gets bigger and heavier, the boiling point of the whole molecule goes up. Why? It's because the bigger the atom, the stronger the intermolecular forces. Those are the little attractions between molecules. And if they're holding on to each other more tightly, you need more energy, a higher temperature to pull them apart and turn them into a gas. So what do these things do chemically? Well, haloalkanes have 2 main moves. The first is called nucleophilic substitution. Basically, a nucleophile, which is just a molecule that's looking for a positive charge, comes in, kicks the halogen out, and takes its place. The other big one is an elimination reaction. In this case, both the halogen and a nearby hydrogen get removed, and that creates a double bond, forming a whole new molecule called an alkene. All right, so that's the story on haloalkanes. Now, let's meet their aromatic sibling, the haloarenes. At first glance, they look pretty similar, but trust me, one tiny structural difference changes absolutely everything. And here it is. This is the crucial difference. In a haloarene, the halogen is bonded directly to an sp2 hybridized carbon. Now, this isn't your standard carbon. This is the type you find in those super stable, flat aromatic rings, like benzene, where all the electrons are shared across the whole ring. It creates a completely different chemical vibe. And this slide just lays it all out side by side. Look at the haloalkane on the left. Halogens on that sp3 carbon. It's a pretty straightforward, weaker, single bond. But now look at the haloarene on the right. That halogen is stuck to an sp2 carbon in a ring, which actually gives the bond a bit of a double bond character. That makes it stronger and shorter. And the result of all that? Haloarenes are way, way less reactive when it comes to that substitution reaction we just talked about. That aromatic ring basically acts like a bodyguard for the halogen. So we know what they are and what makes them different. But where do they come from? Let's take a look at the origin story for these two families, how chemists actually cook them up in the lab. For haloalkanes, one of the best and most common ways to make them is to start with alcohols. And the best method, really, is to react that alcohol with something called thionyl chloride. Now, why is this so great? Because the other stuff you make in the reaction, sulfur dioxide and hydrogen chloride, are both gases. They literally just bubble away out of your mixture, and what you're left with is a super pure haloalkane. It's clean, it's elegant, it's just incredibly efficient.
For haloarenes, though, it's a completely different approach. You have to start with the aromatic ring itself, like benzene, and then react it with chlorine or bromine. But, and this is a big but, this reaction won't just happen on its own. It needs a serious push from a catalyst, specifically a Lewis acid like iron chloride. This is a classic reaction in organic chemistry called electrophilic substitution.
Okay, now let's zoom back out a bit and get back to where we started this whole conversation. What happens when you stuck more than one halogen onto a molecule? Well, that's when you get the polyhalogen compounds, a family that is, without a doubt, incredibly powerful and sometimes incredibly perilous. Let's take dichlorodimethane. This stuff is an absolute workhorse in the chemical industry. It's a fantastic solvent, so it's used in things like paint removers and also in the process of manufacturing pharmaceuticals. Its ability to dissolve all sorts of things makes it super, super useful. Then you've got its more well-known cousins, chloroform and carbon tetrachloride. I mean, both of these were everywhere at one point, used as common solvents, even in things like fire extinguishers. But we now know they come with some pretty serious health and environmental baggage, so their use today is very, very restricted. And that brings us to the big one, DDT. This stuff was a game-changing insecticide. It's credited with saving literally millions of lives from malaria by wiping out mosquito populations. But the very thing that made it so effective, its incredible chemical stability, is also what became its biggest problem. It just doesn't break down. It sticks around in the environment, builds up in the food chain, and poses a huge long-term risk to wildlife.
And this quote really just hits the nail on the head. Halogenated compounds persist in the environment due to their resistance to breakdown. It's a classic double-edged sword. That stability can make a compound perfect for its job, but it also means it can become a pollutant that haunts us for decades. So, useful tools or environmental threats? As we've seen with so many of these compounds, the line is just incredibly blurry. They can be both. And this leads to a massive question for the future of chemistry. How do we keep designing these powerful, incredibly useful molecules while also making sure we don't leave behind a harmful legacy for generations to come? That is the challenge that lies ahead.